chapter, we'll encounter a second type of formal statistical inference, tests of significance. With confidence intervals, we are interested in determining a set of plausible values of a parameter, values consistent with an observed sample. With tests of significance, the focus is on a particular value of the parameter, with an interest in whether the particular value of interest is plausible or may be rejected upon seeing a sample. So there's a connection between confidence intervals and hypothesis tests. The concepts. We'll talk about the reasoning of tests of significance. We'll talk about stating hypotheses. We'll define a p-value and what statistical significance is. We'll describe tests for a population mean and talk about significance from a table. So, confidence intervals are one of the two most common types of statistical intervals. We use a confidence interval when the goal is to estimate a population parameter. The second common type of inference, called tests of significance, has a different goal, and that's to assess the evidence provided by data about some claim concerning a population. So a test of significance is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion or the population mean, and we express the results of a significant test in terms of a probability that measures how well the data and the claim agree. Okay, so the reasoning behind all of this. Suppose a basketball player claims to be an 80% free throw shooter. To test his claim, we have him attempt 53 free throws. Suppose he makes 32 of them. His sample proportion of made shots is 32 over 50, or 64%. So, what can we conclude about the claim based on this sample? It's certainly lower than 80. So, if we use software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter, you can say how strong the evidence against a player's claim is by giving the probability that he would make as few as 32 out of 50 if he really makes 80% in the long run. So, in this case, in 400 sets of 50 shots, there were only 3 times when our shooter made as few as the observed value, 0.64. So the observed statistic is so unlikely that if the actual parameter value is 0.8, it gives convincing evidence that the player's claim is not in fact true. A significant test starts with a careful statement of the claims we want to compare. The claim being tested by a statistical test is called the null hypothesis. The test is designed to assess the strength of the evidence against the null hypothesis. The null hypothesis is often a statement of no difference. For example, in our justice system in the U.S., we assume a person is innocent until proven guilty. So we assume that he or she is innocent unless we find enough evidence against that claim. The claim about the population we are trying to find evidence for is the alternative hypothesis, indicated H sub A. The alternative is one-sided if it states that a parameter is larger or smaller than the null hypothesis value. It is two-sided if it states that the parameter is simply different from the null value. In the free throw shooter example, our hypotheses would be the null hypothesis H sub 0, that the proportion of free throws is 0.8. The alternative is, and that's our claim we're testing, that the proportion is less than 0.8. And in this case, P is the true long-run proportion of made free throws. So here's an example. Does the job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half of the workers were assigned a random to each of two groups. Both groups did similar assembly work, but one group was allowed to pace themselves while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of a job satisfaction. Then they switched work setups and took the test again after 2 more weeks. So everybody did everything there. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. So we state the appropriate hypotheses for performing a significant test. The parameter of interest is the mean of the differences, self-paced minus machine-paced, in job satisfaction scores in the population of all assembly line workers at this company. Because the initial question asked whether job satisfaction differs, the alternative hypothesis is two-sided. That is, either mu is less than 0 or mu is above 0. For simplicity, we write this as mu does not equal 0. So the two hypotheses, the difference between self-paced and machine-paced, there is no difference, so the difference should be around 0. The alternative is that it's not 0. Notice in this case, the word from the example says that the jobs, we're just interested in whether it differs, not if it is greater or less. So the null hypothesis, H0, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against a null hypothesis is called a p-value. A test statistic calculated from the sample data measures how far the data diverge from what we would expect if the null hypothesis were in fact true. Large values of the statistic show that the data are not consistent with H sub 0. So if we get values that are very far away from our hypothesized value, that's evidence that the hypothesized value is not true. So the probability computed assuming that H sub 0 is true, that the statistic would take a value as extreme or more extreme than the one actually observed is called the p-value of a test. The smaller the p-value, the stronger the evidence against HO provided by the data. So small values are evidence against H0 because they say that the observed result is unlikely to occur if H0 is true. Large p-values fail to give convincing evidence against HO because they say that the observed result is likely to occur by chance when H0 is true. So a p-value essentially answers the question, if the null hypothesis is true, that the mean of a population is some particular value, what is the probability that we would obtain a sample mean as extreme or more extreme than the one we got? If a sample mean lands here, it's not that unusual. It isn't that far away from the hypothesized mean. So we can't say that it's different from the hypothesized mean. But if a sample mean lands here, it is unusual because it is far away from the hypothesized mean. It's more likely that the hypothesized mean is wrong and our sample mean provides evidence against. The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. We will make one of two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. We either reject the null hypothesis or fail to reject the null hypothesis. If our sample result is too unlikely to have happened by chance, assuming HO is true, then we reject the null hypothesis. Otherwise, we simply fail to reject. Note, if we fail to reject the null hypothesis, it doesn't mean that the hypothesized value is true. So we should never say that we accept the null hypothesis. All we can say is that there isn't enough evidence to reject it. So in a nutshell, our conclusion in a significance test comes down to two things. Small p-value, reject HO, and we conclude the alternative, and in the context of the problem. If the p-value is large, we fail to reject HO, so we can't conclude that the alternative is true. So we say there isn't enough evidence to reject an. There is no rule for how small a p-value we should require in order to reject HO. It's a matter of judgment and depends on the specific circumstances. But we can compare the p-value with a fixed value that we regard as decisive. This is called the significance level. We write it as alpha, the Greek letter. When our p-value is less than the chosen alpha, we say that the result is statistically significant. Common alpha values are 0.1, 0.05, and 0.01. If the p-value is smaller than alpha, we say that the data are statistically significant at that level alpha. The quantity alpha is called the significance level or the level of significance. When we used a fixed level of significance to draw a conclusion in a significance test, we have, again, two possibilities. The p-value is less than alpha, in which case we reject HO and conclude that HO is true, again in the context of the problem. If the p-value is greater than or equal to alpha, we fail to reject the null hypothesis. So we can't conclude that the claim by the alternative hypothesis is. We'll talk about the four-step process again in the context of tests of significance. So we start. What is the practical question that requires a statistical test? We need to identify the parameter, state the null and alternative hypotheses, and choose the type of test that fits your situation. Then we solve by carrying out the work in three phases. First, we check the conditions for the test that we plan to use. If the conditions aren't met, we can't use the test. Then we calculate the t-statistic, find the p-value, and then we conclude. We return to the practical question in step 1 to describe the results in this setting. So the z-test for a population mean. Once we've stated the question, formulated the hypotheses, and checked the conditions for the test, either you or the software or some software can find the test statistic and p-value by following a rule. And the rule is one that we've used before. It's just looks slightly different. The formula is basically the same as the z-score formula. The differences in this case are that we're using a sample mean, a hypothesized population mean, and the standard deviation of the distribution of sample means. So the alternative hypotheses, for example, if we had the claim that drug A is better than drug B, then our alternative hypothesis would be mu greater than the hypothesized value. Suppose the claim is that a particular method reduces stress, or that costs are not the same as before. They're either lower or higher. We don't know. Okay, before giving an example, I want to just kind of describe what's called a matched pairs design. In a matched pairs design, individuals are grouped in pairs. Then the individuals from each pair are randomly assigned to receive some treatment. Before and after testing is a common type of matched pairs design. So a researcher measures each individual on a variable of interest. Then the researcher gives the treatment, and then we measure the individuals again after the treatment. And we look for the difference in the measurements. So here's an example. Does the job satisfaction of assembly workers differ when their work is machine-paced rather than self-paced? A matched pairs study was performed on a sample of workers, and each worker's satisfaction was assessed after working in each setting. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. So the null hypothesis is that on average there is no difference in the scores in the population of assembly workers, while the alternative hypothesis is that there is an average difference in scores in the population of assembly workers. So the null hypothesis, the mean is 0, which means basically self-paced minus machine-paced is right around 0. The alternative is that the difference is not 0. And we don't know which way that is, but we just are looking to see if it is different. This is a two-sided test because we're only interested in determining if a difference exists, not whether one of the methods scores bigger or smaller than the other. So suppose job satisfaction scores follow a normal distribution with a standard deviation of 60, and then data from 18 workers give a sample mean score of 17. If the null hypothesis of no average difference in job satisfaction is actually true, then the test statistic would be this nasty thing. So we take the z-score then is the mean, sample mean, minus the hypothesized mean, divided by the population standard deviation over the square root of the sample size. So 17 minus 0 over 16 divided by the square root of 18. And that's about 1.2. So for the z-statistic, the test statistic z equals 1.2, and a two-sided alternative hypothesis, to calculate the p-value, it would equal the probability that the z-score is less than negative 1.2 or that z is greater than 1.2, positive 1.2. Remember, we're testing here whether the value is higher or lower. Either will cause us to reject the null hypothesis. So the two-sided, the areas here for z equals minus 1.2 and plus 1.2, the areas are the same, both 0.1151. So a p-value in a two-sided alternative hypothesis test is twice the probability that the z is bigger than either of the values. So 2 times 0.1151, p-value is 0.23. So if the null hypothesis is true, there's a 23% chance that we would see results at least as extreme as those in the sample. So since we saw results that are likely if HO is true, we do not have good evidence against the null hypothesis, so we can't reject the null hypothesis. We conclude that there is not enough evidence that job satisfaction is different for self-paced and machine-paced work. Another example. The survey of study habits and attitudes is a psychological test that measures students' study habits and attitude towards schools. Scores range from 0 to 200. The mean score for college students is about 115, and the standard deviation is about 30. A teacher suspects that the mean mu for older students is higher than 115. So she gives the SSHA to a simple random sample of 25 students who are at least 30 years old. The null hypothesis is that the mean score for older adults is the same as it is for all other students, so it's no different from 115. The alternative hypothesis, which is what this researcher wants to show, is that the scores for older adults is actually higher than 115. So we want to test the claim based on this sample. The hypotheses, the null hypothesis, mu equals 115. The alternative, mu is greater than 115. Keep in mind, the mu that we're interested in here is the mean score for the 25 students who are at least 30 years old. That's what we're looking for. So in this case, we have a one-sided test because we're interested in determining if the sample mean is significantly higher than the hypothesis. So let's assume that these scores are approximately normally distributed with a standard deviation of 30. And let's suppose that the mean score for the sample of 25 older students is 118.6. So we calculate the test statistic, 118.6 minus 115 divided by 30 over the square root of 25. And we get 0.6. So this sample mean is about 0.6 standard deviations above the hypothesized mean. The probability of obtaining a z-score of 0.6 or more is 0.2743. We obtain this value from the table or using software. So that's the p-value, 0.2743. So this is not unlikely. We conclude that there is not sufficient evidence to support the claim that older students score higher on the SSHA. In other words, the sample mean is higher, but it's not high enough to suggest that it's different from 115. Now let's have the same assumptions, but this time let's suppose that we get a sample with a mean of 125.8 rather than what we had before. Is this evidence that the mean of older students is higher? So again, we calculate a z-score, 125.8 divided by 115 over 30 divided by the square root of 25, and we get a z-score of 1.8. So the probability of obtaining a z-score of 1.8 or more is 0.0359. That's the p-value, 0.0359. Again, just to repeat, that's the probability of obtaining a sample mean of 125.8 or more if the population value is exactly 115. So this is not likely to occur by chance. We conclude that there is evidence to support the claim that older students score higher on the SSHA. Now, to get significance from a table. Statistics in practice uses technology to get p-values quickly and accurately. In the absence of suitable technology, we can get an approximate p-value by comparing the test statistic with critical values from a table. You don't have to do this. You're welcome to use the software. So we're going to use, in the previous examples, we found two z-scores. We're going to use table C to approximate the p-value for these scores. We did get exact values, but in this case we'll use table C to approximate them. So with one of the values we had a one-sided test with z equals 1.8. So we look at the row with z star at the bottom of the table, and the row with one-sided p. And then we find the z-score nearest to but not bigger than 1.8. So in this case, 1.8 falls between these two values, 1.645 and 1.96. Under these values in the one-sided p row are the numbers 0.05 and 0.025. So our p-value is somewhere between those two. And the way we want this to be relatively conservative, so what we say is that the p-value for z equals 1.8 is less than 0.05. And that indicates that it's not less than the next smaller value in the table. Okay, so with the one-sided test where we had z equals 0.6, we again locate the row with the critical z values, and then find the z-score nearest to but not bigger than 0.6. In this case, that's to the left of 0.674. So under this value in the one-sided row is the number 0.25. So keep in mind our number 0.6 is actually to the left of that, which indicates that the one-sided p-value is actually bigger than 0.25. So we write that as p is greater than 0.25. So, to review, we talked about statistical inference and defined it, described the reasoning behind tests of significance, describe the parts of a significance test, state the hypotheses, define a p-value and statistical significance, conduct and interpret a significance test for the mean of a normal population, and we looked at how to find significance from a table.